Welcome to VLSI Design's lecture. Today we'll start studying chapter number 8, which is regarding gate delays. We have already studied the gate delay for a NOT in chapter number 7. And in chapter number 7, the same chapter, we came across these expressions for TR and TF. In fact, we derived these expressions. TR, the rise time delay, and for the fall time delay. And we also analyzed that these expressions, when plotted versus CL, the load capacitance, they are like a linear equation, and they can be plotted linearly, where this is the initial delay TF0 and this is initial delay TR0. So actually these two equations are equations of straight line. Today we will see what is the effect of scaling. We call it as small m. We use a scaling factor. If we have this knot, this is the layout diagram for a knot, and this is drawn for m is equal to 1. M is equal to 1 means the aspect ratio of the two transistors is the standard that we are comparing with. And this m is equal to 3. This means the aspect ratios of both PMOS and MOS transistors is 3 times the aspect ratio that we have here. So we want to analyze about the rise time and fall time delay of this knot, which is 3 times in size compared to the standard knot. So we call the delays as TR3 and TF3. Here we call them as TR and TF. Here we introduce a subscript 3 to show that it is for a gate, a knot which has a size m is equal to 3. Right. So let's see what is the impact of increasing the size to 3. TR0 is this one. Let's analyze these two terms in a bit more detail, so that we can derive expression for TR3 and TF3. We already know from chapter number 7 that TR0 is 2.2 times RP-CFET, where RP is the impedance, is the resistance of the PMOS transistor, and CFET is the total FET capacitance at the output of this gate. So this RP is the inverse of aspect ratio of P. We already know that this is inversely proportional to the aspect ratio. If aspect ratio is large, of course the resistance is smaller. So this is obvious, and we have studied expressions for this too. And while CFET is directly proportional to aspect ratio. So TR3 is TR0. Why? Because for TR3 we have 2.2, RP is reduced by 3, and CFET is increased 3 times. So this 3 cancels with this 3, so we are left with the same TR0. So the one term decreases 3 times, the other term increases 3 times, net effect remains the same. And the net effect remains the same. With alpha p, the second term is, we studied in chapter number 7, it's 2.2 times RP. Where RP is inversely proportional to aspect ratio, we increase the size by 3 times, aspect ratio is increased by 3 times, RP is decreased by 3 times, so we have a new RP that is 1/3. We have a new alpha p that is increased by 3 times, so the resistance is decreased by 3 times. So if aspect ratio is increased by 3 times, RP is decreased by 3 times. So we have a new alpha p that is 3 times smaller than the alpha p we had in the case of a standard knot, and for m is equal to 1. So now we have come up with these two expressions for TR3 and for alpha p3. So now we can plug these two terms in here and find this term TR3. Right. So let's calculate TR3 first. So TR3 is, instead of this TR0, we'll put this TR3, because now it is for TR3, TRO3 initial, because this is initial, plus alpha P3 times CL. So TRO3 is the same as TRO, no difference. Alpha P3 is alpha P by 3 times CL. So new rise time delay is this. So the first term remains the same as it was in the case of a standard knot FLM is equal to 1, but the second term is decreased by 3 times. Right. So a similar expression can be derived for TF3. Right. TF0 is 2.2 times Rn times CFET. This we studied in the last chapter, chapter 7, where Rn is inversely proportional to the aspect ratio of n, and CFET, of course, is directly proportional to the aspect ratio of n. So TPO3 initial value of 3 would be Rn by 3 times 3. So this is the same as TP0. TFO3 says TFO. The same as we had in the case of a standard knot with m is equal to 1. Right. What is alpha n? Alpha n is 2.2 times Rn, where Rn is inversely proportional to the aspect ratio of n. This means increasing aspect ratio of n 3 times means decreasing Rn 3 times. So this becomes alpha n over 3. So alpha P3 is alpha n over 3. So now we have come up with TFO3 and alpha P3, and we can plug these values in here to find the new fault time delay for this n is equal to 3 knot. Where is my that is that's it. Right. So TF0, TF3 is TFO3 plus alpha N3 times CL. What is TFO3 is the same as TFO. The initial delay is the same as it was in case of the knot with m is equal to 1. Plus alpha N3 is decreased by 3 times compared to m is equal to 1 knot times CL. So this is the delay caused by a gate which is 3 times in size compared to m is equal to 1. What if this is repeated for a gate which is k times compared to the standard knot? Of course, these 3 terms, this term 3 will be replaced with k, and this 3 will also be replaced with k. So this is how we can generalize it for any value of time. That's all for this lecture. Thank you.